Let's punch some numbers. So we added a new data set. The 32 is now a 63. Not a 62, it's a 63. So make sure you update your data. Make sure you update your data. Now, if you want, you'll notice that when I entered the data in, what are these? What are these 68s and 68s and 72s?
I think that's the one that we just did, no? Or like
maybe from a different class?
I'm thinking it is.
Different class.
Yeah. I'm just trying to think if I can erase it. I can erase that. I can erase that. I don't want to erase it until I know it. There's no Control Z on a TI. So you notice how I was kind of going in order for a while, and then eventually we kind of started going out of order when we got to the larger numbers. You can do a double sort, like if you need to sort the X and F columns at the same time. So what you can do from the home screen, go stat sort A, like you would normally do.
Your L1, L2.
Exactly. Give yourself an L1, comma L2, and what this will do is it'll sort with L1, but it'll pull the frequencies with L2 with it. Does that make sense? Because you don't just want to sort L1. If you sort L1, it's going to group the frequencies up.
Oh, so if you wanted to sort L2 by L1, you can find
exactly. Your mode. Exactly. Exactly. So do you hear what Kelsey just said? If you sort L2 with L1, the mode pops out. Because the largest L2 will rise to the top, or the bottom, one or the other, depending on how you do it. So yeah, that's a clever way to find the mode. Exactly. So now when you go back and you go to your stat editor, the data in L1 is now in order, but the frequencies are now still paired with them properly. So the question I have now, who sent an unusual number of texts today? Who sent, and am I recording? Who sent an unusual number of texts?
0 people did, right?
Zero?
And then the other way far out there one is the 32, right?
Well, it's now 63. Make sure to update your data point. It's 63 now.
Okay.
So, friends, before you answer that question, Raphael, thank you for that answer, by the way. Give me a picture. Give me a picture. So give me a histogram. Yes? Let's do a histogram. There it is. We're scaled by 10. What if we scaled by 5? Is 5 too small? It might be. No, that's not bad. I just changed the scale to 5 instead of 10.5. I did zoom stat, and the scale was automatically 10.5. I just changed it to 5. So the question is, where's the outlier or outliers? Where are they?
They're to the right, right?
Well, okay, I think 63 is a fairly obvious one. But now the next question is, the next one down was 28, which I guess is this guy here. And this is probably also 26. Are they unusually large?
Let's do a box whisker and do that.
Nice, nice. So Tabitha's got a quick, Cassie's saying yes. Who says no? Who says no? They're big, but they're not too big. Just so you know, there's no correct answer at this point. I mean, at this point, we're just saying gut feeling. 60, okay, 63, just in general, in this data set, is 63, I think, is a pretty clear outlier, for sure, for sure. Is the 26 and 28 that are in this bar,
I would say yes.
Yes, so this is great. I see a no and a yes. This is fantastic. And this is what part of the trick is with outliers. There isn't always one rigorous definition of what an outlier is. But we can say for a fact, we can't go with this method, can we? We can't do what we did last time. Why? It's not bell-shaped. The whole point of this, method of the, oh, we can't see what I'm pointing at here on the film. I just said film, that's great, as if there's film in there. You can't use this in general unless your data is actually shaped like a bell. So it's symmetric and unimodal. So this only works if your data is bell-shaped. The problem is you've got a wickedly skewed distribution over there with the text messages, number of texts by frequency. So there is another way that governs outlier identification, and you guys actually saw it yesterday when you were doing that in-class quiz yesterday with the was it yesterday? I think it was yesterday or Monday with the snowfall data. Right? I had you run a box plot on the snowfall data, and I said, now go back in and run the modified box plot. Remember the modified box plot? So let's slap a box plot on top of this bad boy. So let's put a box plot up there with the histogram. So turn plot 2 on. Okay, on. Now I'm going to start with just a normal box plot, not a modified one. We'll come back to the modified as per Tabitha's request.
Thank you.
Oh, yes. And there it is. Love this. Love this thing. Love this thing. I'm actually going to change some stuff to make things easier to see. I'm going to change, you guys get the similar graph? What I'm going to do is, I'm going to press the window button, and I'm going to make x-min -5, which I know doesn't make any sense, but all that'll do is it'll give us some more wiggle room on the left side. And now I'm going to do something we don't often do. I'm going to turn that vertical axis off, because it's kind of getting in the way of what we're looking at on the left side of that box plot. The way you do this, and you don't want to do it very often, you press second zoom, and then you see where it says axes on, axes off. We'll turn that off, just real quick, and then we'll just get the histogram with the box plot. And the reason I wanted to do that was the y-axis was getting in the way of that little teeny tiny whisker way out there on the far left. So now we can actually see it a little bit better. Fair enough? Good, good. So what the hell? That's like the coolest box plot ever. Because you have this little tiny whisker on the left side and this ridiculously long whisker on the right side, and then you've got this little tiny partial box here, and then this wider box here. Tabitha, I'm thinking of your mid-quartile. There's your mid-quartile, which doesn't tell us anything really. But it does tell us that 50% of you sent a very concise number of texts between 0 and, say, it looks like 0 and 2. There's half the class right there. Here's the other half of the class. So the half of the class that sent very few texts all sent roughly the same number of very few texts. But the half of the class that sent the most text have a wickedly variant number of texts sent. That make sense? You guys buying that logic? Perfect, perfect. So now the question is, I don't think, so Raphael, back to your original gut feeling. You said 0 is an unusual number and 63. Do you think 0 is unusual anymore?
Not really.
Now 0 is not unusual anymore. Remember, the definition of outlier is atypicality. 0 is not that atypical. I mean, honestly, 0 is, look, 0's in this bar. 0's in the modal bar. So 0 is pretty typical. Yeah, 63 is definitely off base. How about these guys? Change that box plot to what's called a modified box plot real quick. And then we'll come back and explain to you mathematically what's going on with that, okay? So, second stat plot, plot 2. Change this bad boy. Oh, Chessa, that's the guy you want for the OJI you were asking about. That guy right there. Just so we're already in here. You get a little thing called a mark at the bottom there. That's just saying if we have outliers, we're going to put that symbol down to mark them. Now press graph. Look at that. The TI is saying that the only outlier indicated is the furthest right one, which was the 63. You can get to it by pressing trace, jumping up onto the curve or the plot, and then scooching to the right. There's your median. Oh, your median was actually 5, not 3. Keep going. Third quartile was 16. Notice when you go out to there, it says x equals 28. Yesterday with the box plots, as we jumped around the box plot, it said min x, q1, median q3, and max x. There are now more than 5 numbers because you have an outlier. So that x, somebody asked me in the last class, what does that x mean? And then somebody else answered it. What does it mean when it just says x? X equals 28. What does that mean?
Is that like the end of the typical data point?
Beautiful. That's exactly what it is, Cassie. It's the last data point it's the largest data point that's typical, the end of the typical data points. Well, actually, I want to edit that statement a little bit. It's the last of the typical data points. It might not be the end. There might be room for more, but we don't have any of them. Now the question is, how do we define room for more? What guideline is the TI using to decide that 63 is too big, but 28 is not? And that's method number 2. Jess, you asked, you're like, wait a minute, we got this bell-shaped one. But how about when the data is not bell-shaped? So here's what the TI is doing, just so you have an understanding. Yesterday, if you remember, I'm going to turn this plot back on. And you can say, no, I don't remember, of course. But when you guys had your box plots from snowfall up on the board, I walked around and I said, that one had outliers, that one didn't, this one did, this one did, this one didn't. The reason I'm doing it is, this is what the TI is doing. It's measuring this distance, this IQR that's right here. It's taking that and increasing it by 50%. We're going to break this down more formally in a second. And then it's stacking that on Q3 and below Q1. So essentially, when it does that, I'm going to throw up some squiggles here. That is what you just said, Cassie. That's the end of the typical data points. So that's as large as it can be until it's considered then too large. And then, oh, excuse me, so over here, that would be as small. That's negative, so it doesn't make any sense. But that's small. Anything past that's now too small. So let me just walk you through. I like to walk through this method just real quick manually. It takes about 5 minutes to walk through it so you understand those two purple squiggles and how they're calculated, but also how they tie into this one. Because they do have an analogous kind of feature with this one here. Please show me.
Sorry, so on Monday when you were doing that,
Yes, ma'am.
If you can take 50% and that, then they might have one outlier, but if you can do it twice, they have more than...
Yes, and I'm not saying, very good, and I'm not saying that this method agrees with that method perfectly. You can use, so basically, let me answer that question in context, that's okay, Shelby, great question. Here, Mom. Eraser. I'm going to call this the IQR method, just because it seems to be known as that. So here's method number 2. Now, this will work for any data set, not just skewed. So you can also use this on bell-shaped data, which is kind of what students kind of like this because it's more universal. It's got like kind of a more universal application. So this IQR method, you start by finding that IQR. And the definition of an IQR is kind of like the mid-quartile, but it's instead of an average, it's a distance. It's Q3 minus Q1. It's how far apart the quartiles are. So if you're looking for an analogy to the other method, it's how far apart one standard deviation is. It's not equal to that same number. It's not equal to that same number because in bell-shaped data, what percent of the data is within one standard deviation?
Is it 68?
Be brave, 68, right? 68 bell-shaped data. What percent of the data is between these in all data sets?
50.
Exactly half. So there's definitely a difference there, but it's analogous in method to that. So there's an analogy there. Okay. So for our data set, we'll do a little asterisk here. For our data set, our Q3 is 16, and our Q1 is 1.5. So our interquartile range, oh, I didn't ever, yeah, interquartile range, you have to write that down if you don't want to, is 14 and a half. It's 14 and a half. That's how much distance is between the 25th percentile and the 75th percentile. 14 and a half texts different between the 25th and the, yeah, I know, it's kind of strange, half texts. But that's, you have an even number data set. Now, when we have bell-shaped data, we then multiply that by 2, as Shelby said, to pick up more data. You also multiply this guy by something over here. I should call this step A maybe instead of 1. But it's not 2 that's used commonly. It's 1.5. For what reason, I'm not entirely sure. But like I said, these aren't laws. These are just definitions we've created. So you take 1.5 times that IQR, that interquartile range. So you do 1.5 in our example, asterisk. You do 1.5 times 14.5. So that's going to be 14 plus half of 14.5, which is 7.25. 21.75. Check my math on that, would you? Make sure I did that right.
1.75, yeah.
Good, did it right? Okay, good. So that's texts. 21.75 text messages. It's hard to say slowly. So if you will, that's kind of like 2S.
So that's basically 75% is what you're getting?
Ish. That's a great question, Raphael, and I'm saying ish. The reason why we can make the claim about like 95% and 68% with bell-shaped data is because we know where the data is in a bell. We don't know where the data is on a box plot. We know it's broken into 4 regions, but we don't know exactly where it is in those regions. That's an awesome question, and there's no simple quick answer for it. But a fantastic question nonetheless. What it essentially does is it's allowing for wiggle room as to where the data is. So you're trying to stretch it out, not on a fixed percentage, but just giving a nice wide variation to let the truly extreme values go off. And please realize too, friends, 1.5 is the most commonly used multiplier. Sometimes they use 3, sometimes they use 2. This is just the one your TI is using and the one that I've seen most often in journals. Go ahead, Tabitha.
So, any number that's 1.5 times the interquartile range is considered an outlier?
Almost. 1.5 interquartile ranges from a certain value. And this is the part that's a little bit weird. When you have 2 standard deviations, you add and subtract that from the average, x bar. We don't use x bar with box plots. So you would think, what's analogous to x bar with a box plot? What's the analogous measure? The median, right? But it's not what's used to do it this way. Check this out, it's a little bit strange looking. Your typical data, watch this. Remember when I did it with my hands? I went plus 50%, and then I stacked it over here. Do you see what I'm adding that 1.5 IQR to?
The end of the
The end of Q3, and then when I do it and come down here, I'm subtracting it from Q1. So that's kind of the oddball thing. The typical data is going to be either Q1 minus that 1.5 IQR. That's the low end of it. The high end of it is going to be Q3 plus that 1.5 IQR. That's the oddball move. And again, I'm saying, these aren't following natural laws. These are humanly created rules. So this is the one that they've created for IQRs. So all we've got to do is now add and subtract those numbers and see if any of our data falls outside of that range of typicality. Now, one of those numbers is ridiculous for us. It's negative, right? Our Q1, I forget what it is now. Oh, there it is. Our Q1 is 1.5. So if you do 1.5 minus 14.5,
minus 21.75.
21.7, sorry, using the wrong number. Minus 21.75, it's still negative 20.25. My point is that it's negative. My point is that it's negative. You can't have a negative number of text, which means, Raphael, we've quantifiably shown why 0 is not atypical, because 0 is well above negative 20. Here's the interesting thing, though. Where does the top get cut off? Well, what you do is you go over to Q3, once I turn it back on. Q3 is 16. So you take 16 plus 21.75, and you get what, 37.75? Cassie, finally, I've answered your question. That's the number that separates typical from atypical. If anybody said 38 texts, you would have been atypically large. 40 texts, atypically large. 50 texts, 63, atypically large. But 28, which was our next smallest one, 28 is within the typical range. Does that make sense? 28 within the atypical range. Is that fair? Is that good? So Jess, to answer your question, there's a second method. You can use this one all the time, including bell-shaped data. It's just that research journals tend to use the bell-shaped one more than the other one. The other ones, it's great when you have a bunch of box plots laid side by side, these great outliers and markers. They're kind of interchangeable because they do serve the same purpose. This one's just more readily accessible for more types of data. Is that fair? Please, this is the only time you will do this kind of arithmetic on this, because your TI does it for you. When you select so from now on, friends, whenever we draw a box plot in our TI, let's draw a modified one. That way, if there are outliers, it'll find them for us. How's that sound? Yeah? Let's just do the modified one. I mean, you know why it works now. That's important. But it's not important to test your arithmetic all the time. I don't think so anyway. Is that fair?
What was the modified one?
It's the one. It's the first item. Let me get down to you here. It's this guy right there.
Okay.
So when you hit graph, you'll see it out there. See, there's your Cassie. I answer your question again. There's 38.7. Yeah, 37.75. That's your cutoff. That's why I had to edit my answer to you, because that isn't the limit. That's just our limit on our data. That's the actual limit. Cool? Makes sense? You can have more than one outlier, FYI. You can have more than one. I mean, suppose somebody else, let's just throw one more data point in there. Let's throw it at the bottom. We have a 63. Let's say somebody had a 52 as well. Okay? You can have more than one. You can have outliers on both sides. That exists too. When I did my data last weekend, when I was doing the, hello, hey, Charlie's here. The party can begin. So what we had last week, I actually had symmetric outliers. I had very small and very large data points, which have interesting effects on data because they don't change the average at all, but they change the standard deviation greatly. So there's all kinds of ins and outs of outliers. But we'll deal with that as we go through the course. What I want to do right now, I have another in-class quiz. I thought this might be a kind of a cool place to do an in-class quiz. Charlie got here just in time for that. You haven't even been caught up, Eric. Work together if you want on this, or work individually if you want on this. Basically, I pulled some data off of SigAlert website, which was speeds of cars tracked on a section of Highway 405 in LA. I don't know when, I don't know exactly where, time of day and stuff like that, but these are the speeds in miles per hour. So basically what I'm going to ask you to do on this is generate a histogram of your data and let me know if any cars were traveling unusually, atypically. And by that I mean too fast or too slow. Atypical can also mean just different than the rest, but take a look at the data. Take a look at the data. Give me a look at the data. All right, I'll wander around with you. Make yourself a modified box plot. Make yourself a histogram. Calculate some averages if you think an average should be calculated.